Hello, this is Joe Padergo, a student in Dr. Cooper's Engineering 1166 class, and I'm going to be discussing the idea of using nanotextured titanium for an improved bone-to-implant interface. To give you a brief overview, first I'm going to discuss current joint replacement and use the example of hip replacement. I'll touch on the biggest problem of current methods, wear, and then describe the solution, nanotextured titanium. I'll detail its advantages, the experiment used to determine its success, the materials used, how the titanium is textured, and finally the results of the experiment. To begin with, I'll provide a brief background to joint replacement itself. A joint is formed where the ends of two bones meet, as seen in this picture of a knee, which is where the femur and tibia meet. As the joint ages, the cartilage between the bones can become damaged and the bones can rub against each other, causing pain and limiting movement. Surgery can be used to replace either the entire joint or parts of it, depending on the extent of the injury. Let's take, for example, the hip joint. The hip joint is a ball and socket joint. The ball of the femur is inserted into the socket of the hip. Osteoarthritis, or the breakdown of cartilage, can weaken the joint. If total hip replacement is required, a surgeon will remove the ball of the joint and replace it with a metal ball on a shaft, inserting the shaft into the femur. Also, a metal cup will be inserted into the socket of the hip. The risks associated are blood clots, nerve damage, infection, and wear. The biggest problem faced by people with hip replacements is wear. Wear occurs due to the metal-on-metal rubbing of the artificial ball and socket. Over time, tiny particulates build up and loosen the ball, as seen in the picture. Current hip replacements only last up to 10 years, after which another operation may be necessary. Thankfully, studies show that nanotextured titanium implants can improve joint replacement. A laser creates micron and submicron peaks and ridges across the titanium, leading to advantages such as better cellular adhesion, less risk of infection, and reduced wear. The current smooth implants are difficult for cells to grow on. This compromises the function of the implant and leads to a greater chance of rejection by the body. Certain textures created by a laser on the titanium allow osteoblasts, cells necessary for the growth of bone, to adhere to the surface. The spacing of the peaks and ridges is controlled by the titanium sapphire laser system. Textured titanium also decreases the chance of infection. Infection occurs because the implant is seen as a foreign object and the immune system attacks it. The textured titanium allows the cells to bind to the implant, allowing the body to recognize it as its own. Wear, as previously discussed, is a problem for current joint replacements. A tissue capsule is created around the implant, and friction develops between that capsule and the metal. This limits joint function and over time will loosen the implant. Since osteoblasts adhere to the titanium when it is textured, no capsule is created around the implant, and therefore little to no wear is created. This will hopefully lead to much longer artificial joint lifespans. Now for the experiment that determined these properties. First, titanium sheets were textured with a laser. Then, both those sheets and controls were placed in wells implanted with rabbit osteoblasts and human mesenchymal cells, which can differentiate into osteoblasts. The proliferation, or cell growth, was determined after both 1 and 3 days. The most important material in creating this experiment is the Spectraphysics titanium sapphire laser system. It consists of a crystal of sapphire doped with titanium ions, giving it the thermal capacity to withstand high-intensity lasers and the ability to generate pulses on the order of femtoseconds. It is capable of 1,000 pulses per second, with each pulse having the duration of 45 femtoseconds, or 4.5 times 10 to the minus 14th seconds, and producing over 2 million joules of energy. It is, however, expensive, costing around $100,000. This is a diagram detailing the titanium sapphire laser system's pathway. The beam comes in on the far left and goes through the titanium sapphire crystal, off mirror 2 and 1, back to mirror 2, through the crystal again, off mirror 3, and the rest of the way through this system of mirrors and into the gland calcite laser polarizer. This is a crystal used to separate non-polarized light into two separate polarized beams. It is used specifically in junction with high-powered lasers and contains a prism angle close to Brewster's angle, which is the angle at which light is perfectly transmitted with no reflection. It is relatively cheap, around $1,000. To create the textured surface, A sheet of smooth titanium is placed in a vacuum chamber and mounted on a computer-controlled XY stage, which can move the sample in both the X and Y planes. It is then exposed to laser pulses from the titanium sapphire laser system while being moved by the XY stage. The stage can be programmed to vary its speed, leading to different pulse rates on different parts of the titanium and thus creating a varied surface, as seen in the picture. The results of the experiment conclusively showed that both osteoblasts and mesenchymal cells adhered better to the textured surface than the smooth surface. The cells attached themselves and formed bridges to neighboring ridges. The textured titanium remained hydrophilic, which is surprising because chemically treated metal usually becomes hydrophobic. The fact that it remained hydrophilic is promising because hydrophobic metal could not be used in the body. In conclusion, the nanotextured titanium provides many advantages over current joint replacement methods, including reduced wear, cellular adhesion, and less risk of infection. It is certainly a cost-effective procedure, paying for itself in only a couple of operations. It is a novel technique that is still in its experimental phase, though it promises longevity for joint replacements. In addition to all the sites that aided me in this project, I'd like to especially thank Dr. Nair, an assistant professor of orthopedics at the University of Connecticut, and Dr. Laurentian, the Dean of Medicine at the University of Connecticut, for their great advice and patience. Does anyone have any questions?